Okay, it says it's recording. All right, today we're going to talk about section 3.2 and 3.3. 3.2 is domain and range, and 3.3 is properties of graphs. Again, this is a relatively short section compared to other sections we've done, particularly since you have the notes. For domain, there are exactly two different cases where we might have a problem with a domain. We're going to talk about both of those. The first reason we might have a problem is This is math, not English. Fractions. The first reason we might have a problem is. Yes, that's right. So the denominators, which is the bottom of a fraction, cannot equal 0. I'm laying it out for you. If there is a denominator, one of the issues you can have with the domain is when that's equal to 0. The other one is a square root function. And in this case, with square roots, I have a pencil you can borrow.
Okay.
I'm going to ask you not to throw things in my class. That may be the case, but you could have hurt someone else. All right, square root functions. So with a square root, the radicand, the stuff underneath the radical symbol, must be greater than or equal to 0. Any questions? Okay. Example 1. We want to determine the domain of f of x equal to 3 over x plus 2. So, how do we find the domain? Let me go back. There are two cases where we have a problem with the domain. Fractions or square root functions. Okay, let's ask it again. How do we determine the domain? Okay, let me back up again. There are two problems we can have with a function and its domain. Fractions or square root functions. Which one of those do we have here? We have a fraction. Okay, so now that we've got that set up, what is the condition that causes us to have a problem with fractions? If the denominator is equal to 0. So what do? Let's set the denominator equal to 0. So set x plus 2 equal to 0 and solve for x.
It can be less than 0?
It can.
It just cannot.
It can't be exactly equal to 0. Because that would cause us to have division by 0, and that's against the rules. That's like the only cardinal sin in math is you can't divide by 0. Okay, so how do we solve this equation for this new equation for x? Subtract 2 from both sides. So x would have to equal -2. So that's being excluded. That's the only thing that cannot be in our domain. So if we were to write that out, our domain would be all the numbers from -infinity up to -2, right? Not including -2 because it's not in there. And then all the numbers from -2 to infinity. And then we group those two sets with a union. So it can be in either one. So x can be any value in the real numbers except -2. Do you have a question?
Well, just how would you clarify that it's not equal to 0? If you don't, if you sit negative.
This is how we clarify it. So the only thing that causes our denominator of our original function here to be equal to 0 is if x was equal to -2. So we're saying that our domain, which is the set of all the inputs that are possible, is everything except -2. So we don't even allow that to be a possibility. Good question. Okay. That's not all. Something else I want to show you. Not that. Okay. There we go. So if we were to draw out this domain, what would it look like if we were to graph it? Just the domain. Well, we know we'd have a hole at -2. We'd have an arrow that went to the right and an arrow that went to the left. So it's literally every real number except that one. Something else I want you to notice. How many issues did we have in our domain? How many points did we have excluded? Just the one. And how many holes did that cause? One. And how many different pieces were in our domain? How many different intervals? 2. So one hole created 2 different parts of our domain, 2 different intervals. You'll see that sort of accelerate in the next example. Okay, example 2. We want to determine the domain of 3x plus 2 over x squared minus 3x plus 2.
Damn, that was a lot.
Thanks for saying that right into the microphone. No, I'm not just going to not edit it out. I'm going to increase the volume at that point for maximum embarrassment for you. So, what are 2 issues we can have with the domain? Square roots and fractions. Which one do we have? I don't see a square root in there. It's a square. Square as opposed to a square root. So we have a fraction. And what do we care about? We care about the denominator being equal to 0. So if I were to rewrite this, my denominator, can I factor it? I'm about to factor this denominator, the whole thing. So I have graded that part of your tests, so I might go back and revisit factoring if you don't remember how. So we're looking for the factors of 2, that when we subtract them, we get -3. -2 and -1. So x minus 2, x minus 1. So the only thing that can cause this denominator to be 0 would be what? 2 or 1. So we'll set x minus 2 equal to 0 and x minus 1 equal to 0. So if we add 2 to both sides of this one, we get x equals 2. And add 1 to both sides of this one, and we get x equals 1. So really what we're saying is x cannot be 2 and x cannot be 1. So this time, before I do the interval notation, I'm actually going to draw our graph because I think it'll be more instructive. So -3, -2, -1, 0, 1, 2, and 3. Where are the holes? At 1 and 2. So we have everywhere else is included, right? So we go from -infinity to -infinity to 1. And then we go from 1 to 2. And then from 2 and beyond. 2 to infinity. Notice I use parentheses with all of these. Why is that? One and 2 are the only values that are not included. Since they're not included, we have to use parentheses. Any questions? No one? Stephanie, you good? Sure.
So if it was included, what would it look like?
So if it was included, it would be a closed circle, and then we would have a bracket there. But since we're excluding those values from the domain, they're really never going to be included with a fraction. Remember, with a fraction, we're saying it cannot be equal to. Now, with a square root, we're going to say it's greater than or equal to. So that equal to will guarantee that we'll have a bracket. Speaking of that, let's look at example 3. We want to determine the domain of f of x equal to the square root of x plus 3. So what are 2 types of issues we have with domains? Fractions and square roots. Which one of those do we have here? We have a square root. And what is the condition on the square root? What has to be greater than or equal to 0? The radicand, the stuff inside. So what do we set? X plus 3 is greater than or equal to 0. It has to be that thing, whatever's inside there, has to be bigger than or equal to, greater than or equal to 0. And then we solve for x. Just an inequality, we've done that. right? How do we do it? Subtract 3 from both sides. And we get x is greater than or equal to -3. Okay. So, what would that interval be? What would our domain be? It's all of the numbers bigger than or equal to -3. So the equal to gives us a bracket. -3 to infinity. And remember, we always use parentheses with infinity and negative infinity.
Those are less than symbol, would infinity be negative?
Yes. And it would go first. We would have the negative infinity up to that certain point. Good question. Any questions? Abraham, you good? Joe, you good? Other Joe's not here. All right, let's move on to example 4. This is my way of trying to trick you, except I'm literally going to tell you what it is, so I'm not really tricking you. I'm trying to prepare you for when you see this on a test or homework. We want to determine the domain of f of x equal to 1 over the square root of 3x minus 1. So what are the two problems we can have in a domain? Say it loud. Fractions and square roots. What do we have here? We have both. This is the first time we've seen one where we have a fraction and a square root. So what do we do? No. So when we have a fraction and a square root, we know that the denominator can't be equal to 0, right? But we also know that the inside of the radicand has to be greater than or equal to 0. So we need to have 3x minus 1. We know it can't be equal to 0, right? So rather than being greater than or equal to 0, just greater than 0. So we treat it exactly the same as we would with a square root, except it can't be 0. We just take that condition away. Did that click for you, D?
Yeah, only when it's in a fraction.
Only when it's in a fraction, for sure. And when I say only when it's in a fraction, I really mean only when it's in the denominator of a fraction. Because if that were in the numerator, we'd have to check to see, okay, is this part greater than or equal to 0? And then you'd have to check the denominator to make sure it wasn't 0. So you'd have multiple conditions. So we have 3x minus 1 is greater than 0. How do we solve for x? Add 1 to both sides. And we get that 3x is greater than 1. Divide both sides by 3. And we get x is greater than 1/3. How do we write that in interval notation? It's all the numbers bigger than 1/3. 1/3 to infinity. Parentheses on both. This is the case where if we have a square root, that we end up with a parenthesis rather than a bracket because it's not included. Any questions? Straightforward. Up and down for yes, side to side for no. Okay, let's talk about some graphs. We want to use the graph in example 5. to determine whether the relation is a function as well as its domain and range. So first question, is this a function? Why do you think so? It would pass the vertical line test, right? There are no repeated x values. So yes, it's a function. What about our domain? What are our possible x values? That's left or right. So the farthest left we can go is -2. And -2 is included. Notice that we have a filled in circle there. And it goes all the way to the right to 1. Is 1 included? It's not, because there's an open circle, so we use parentheses. Now, looking at the range, what is our lowest possible y value? Okay, let's look at this scale. So that's -10, and there's only 5 lines between. So each mark is -2. -1. And notice that it's included because we have a filled in circle, and it goes up to 2. This is our biggest value here, and it's not included, so we use a parenthesis. Questions, comments, concerns, criticisms? Cheeseburgers? Starts with a C. I'm just adding it to my list. So now I'm going to say comments, concerns, questions. Has the same hard K sound. Criticisms, cheeseburgers. It is a C. But it's the K sound, the K sound. No, the other words, questions, yeah. Like KW, yeah. Anyway, again, not English class. Example 6. Let's do actual math. Is this a function? Yes, it's a function. What's our domain? Chris, why do you say that? The arrows to the left and right show us that it goes on forever in both directions. The range is similar, but we have a minimum down here, right? What's our lowest possible value? -2. And it goes up to infinity. You guys are so smart.
So since there's no like open or dot, closed circle, whatever you mean, you just assume that it's included.
So since we're going from -infinity to infinity, this is what's called a continuous function. There are no holes anywhere. So every point that's possible is included, including in the range -2. So yes, assume that everything's included unless you see a hole. Other questions? Okay, the next thing we want to talk about is determining intervals where we have the function increasing, decreasing, and constant. And this little example here, this graph, I want you to treat it like a roller coaster. I know we talked on the first day my love for roller coasters. We have some hills, we have some stops, and then we have another hill, right? Okay, we want to determine how the function increases, decreases, or stays constant. And we use intervals of the domain to discuss that. So we do it from left to right on the x values, and we track the y values. So we have three categories here. We have intervals where we increase, where we decrease, and where we stay constant. And you're not always going to have all three. A lot of times you'll just have to put none on those portions. So I say increasing, decreasing, and constant. So if I jump on my graph at -2, what is it doing as it goes to the right? It's going up. It's increasing. Where does it stop increasing? X value. 0. So from -2 to 0, we are doing what? We're increasing. And we always use parentheses for this, no matter what, whether it's included or not. Okay, so I've gone to this point. So I'm going to jump on my graph right here at 0. What does it do from 0 to 2? It's constant from 0 to 2. And then what does it do from 2 to infinity? We increase from left to right from 2 to infinity. Are there any intervals where we're decreasing? No. So we just write none. Not bad, right? So far? So what do we use to determine the intervals of increasing and decreasing? Which values do we use? We use x values, and which values do we track the increasing, decreasing, or constant? The y's. Okay. Example 8, we're going to do the same thing. Increasing, decreasing, and constant. So where do I jump on my graph? What's the farthest thing left? What is it? Down here. What's the smallest part? -infinity. And so I go from -infinity to, where does it change? It changes at -1. So from -infinity to -1, we're doing what? Increasing. -infinity to -1. And then I'm going to jump back on at -1. What does it do on its next interval? It's decreasing. And where does it decrease to? -1 to 1. And then at 1, what do we do to infinity? We increase to infinity. So up here, 1 to infinity. Are there any intervals where this graph is constant? No. So there are none. And that is actually the most common occurring thing. It's almost always the case that you're going to have nothing constant, especially for something that is continuous like this. Any questions? Okay. The next thing we want to talk about is local minima and maxima. So, a local maximum occurs when the function values, that's f of x, go from increasing to decreasing. What does that mean practically? It goes from going up to going down, right? We get a peak, which would give us the maximum, right? A local minimum occurs when the function values f of x go from decreasing to increasing. So nothing changes here about finding increasing, decreasing, and constant. We still want to find those intervals. But now we add on a layer where we say, okay, well, where does it go from increasing to decreasing so we can find the maxima on that local interval? And where do we find the minima where it goes from decreasing to increasing? So this graph here, we have increasing, decreasing, and constant. Jump on the roller coaster at negative infinity. Where do we go to? Where does it change? At negative 2. So we're increasing from negative infinity to negative 2. And then from negative 2 to 0, we're doing what? Decreasing. And then 2 to infinity. What are we doing? Sorry, not 2 to infinity. 0 to infinity. We're increasing. Remember, it's the x value, 0 to infinity. I just messed up there. So 0 to infinity. Do we have any intervals where it's constant? No. Just intuitively, before we're not changing pages yet, we're not done. Intuitively, can you look there and say, yeah, there's a maximum there. There's a local maximum at one point and a local minimum at another. Anywhere you see a hill like this, that's a maximum. Anytime you see a valley like this, that's a minimum. So at negative 2, we have a local max at x equals negative 2 because we go from increasing to decreasing. And what is our y value at that maximum? 2. So from here to here, our maximum is right there at 2. And our local minimum? At 0. Not 0, but x equals 0. That's where we go from decreasing to increasing. And what's our y value? Our y value is 0. Any questions? Nobody? Y'all are just sitting on go, trying not to fall asleep. Panda Express keeping you up late. Sometimes food does that to me too. All right, example 10. We're putting everything together now, like the whole lesson into one. We want to determine the domain, the range, intervals of increase, decrease, constant, local minima, and local maxima. Now, we're not guaranteed to have every one of these things, but we want to check for them. Okay? Let's start with our domain and range. Can we do that? What color do y'all want me to use? Pink, okay. So our domain, what are our possible x values? -1, not included because there's a hole there, to infinity. And our range, what's our lowest possible y value? -3, and it goes up to infinity. So I'm going to write out increasing, decreasing, and constant. If I jump on my graph roller coaster here at -1, from -1 to what? To 0. What are we doing? -1 to 0, we're decreasing. And then we jump back on at 0. What do we do as we go to the right? We're increasing to infinity, right? So 0 to infinity. Do we have any intervals where we're constant? No. Do we have any maxima? Infinity is not a number. It's a concept that says we're going on. It keeps going, so that's not a maximum. A maximum is a place that happens where we're going from increasing to decreasing. That's how we get a maximum. Do we have any where we go from increasing to decreasing? No, we do not. So there are none. What about minima? So it happens at -3, or when x equals 0, our minimum is y equals -3. And something that we'll talk about in more formal detail as we move along through, particularly chapter 5, I think, is that this local minimum is not just a local minimum. It is the global minimum. It's the minimum for the whole graph. And we'll see that as we move on. But not today. Any questions? If I turn you loose on this, you're going to be able to do all of these things, right? Without ever asking me any questions.
How did you get the -1 of the decrease?
So we use the x values. And so the x value where it starts is -1. So it goes from -1 and it goes down. That's decreasing. Good question. Are there others? No other questions? I don't have to worry about y'all thinking we're done because you know that we have more. Okay, let's talk about piecewise defined functions. So a piecewise defined function is a function that has a different formula for different parts of its domain. Michaela, you're looking like, what is going on here? So what these say is that we have this function, okay, just a function, but if x is less than -2, it behaves like x plus 1. What does x plus 1 look like? What is it? No. What does the graph of x plus 1 look like? What kind of function is it? Guys. No. What's the power on x? 1. When the power on x is 1, what kind of function do we have? It's linear. Thank you, Christina, for bailing us out. Why is it linear?
Oh, I don't know. I just can't.
Bye. I'm done. Okay, it's linear because the power on x is 1. Basically what that means is we plug in an x, we get out of y, the rate of change of that is always the same. What is the rate of change on a linear function? It's the thing in front of x. It's 1 in this case. Yes. You remember that y equals mx plus b business? It's the slope. The slope's always the same. So this looks like a line with slope 1. Okay? And that's true as long as the x values are less than -2. But if the x values are greater than, and it should say, and you can correct this, greater than or equal to -2. Not sure why that doesn't say that. Don't act too exasperated. Things happen. It looks like -2x minus 3. Now, at this point, in this particular example, I don't care what it looks like. We're not going to graph it. We could graph it. We could do it on our calculators. We could graph it by hand. We could jump into Desmos and graph it. But all I'm asked to do here is to find specific values of the function. And if you remember back to the section on function notation and evaluating functions at specific points, we take the thing on the inside and we plug it in for x, right? So we want to find f of -3 first. So -3 is in the domain. Do you agree with that? Which piece is it in? You okay? Okay.
My eyes get watery whenever I yawn.
I was going to say, this is nothing to cry over. Okay. -3 is in our domain. Which one of these pieces is it in? Is it less than -2 or is it greater than or equal to -2? It's definitely less than -2. Okay. Now that we agree on that, that means that this is the formula we use. So in place of x, we put a -3. So we have -3 plus 1. And we get -2. So the ordered pair that we would use here would be -3, -2. And this would be true for any of the x values that we could think of. It would build these list of ordered pairs, an infinite list actually. What if we find f of -1? We still need x equal to -1. Which interval is -1 in? It's greater than -2, right? Yes? Okay. So that means we use the second formula. So we'll say -2 times our x, which is -1, minus 3. What's -2 times -1? And 2 minus 3? -1. So -1, -1. I would like for you to take just a moment and find f of -2. And we'll come back momentarily and go over it. Okay, what do we get, guys? Minus 3. Okay, so how do we know that we're using that second formula? Negative 2 is greater than or equal to negative 2. Okay, so negative 2 times negative 2 is 4. 4 minus 3 is 1. So our ordered pair is negative 2, 1. Questions, comments, concerns? You will definitely see a piecewise function on your test. Just warning you. All right, last example of the day on this fine Wednesday, the 9th of April. We have 3 different values or 3 different formulas for this function. So f of x is equal to x squared if x is less than or equal to 1. It's equal to 3 if x is between 1 and 2, including 2. And it's equal to x if x is greater than 2. So we need to graph all 3 parts. We'll do them a part at a time. So we're looking at values less than negative 1. Okay, and it's the square of those things if it's less than or equal to negative 1. So I'm going to create a little table. So we know that we want values less than negative 1, right? Less than or not negative 1, less than or equal to positive 1. So let's do, I don't know, 1, 0, negative 1, negative 2, and negative 3. Do you agree that all of those x values are less than or equal to 1? Yes. And let me rewrite this x squared. I'm going to say f of x equals x squared. Okay, what's 1 squared? 1 squared is 1. What's 0 squared? Okay, what's negative 1 squared? 1. Negative 2 squared? Try again. 4. And negative 3 squared? 9. So what we've done is we've found 5 different points that we can graph over on those coordinate axes for this portion from the left to 1. Okay, so negative 3, 9. Negative 3, 9. Negative 2, 4. Negative 1, 1. 0, 0. And 1, 1. Do you agree with that? Do you agree with those points?
Yeah.
Yes. So I'm going to connect those dots with a curve. It's not perfect, you see. Oh, it's even less perfect like that. No. I'm not going to let it do it so bad. Again, it continues on to the left to negative infinity, and it's going to have that same general shape. So, we've done that part. Now it says that the function is equal to 3 if x is greater than 1 and less than or equal to 2. So we know that 3 is not included, 1 is not included because it's included in the bottom one. And it's constant at 3 all the way to 2. That's our constant part. And then we know that when x is greater than 2, let me mark this one out. our y value is the same as our x value. It's equal to x. So 2 is not included, but 3 is included. So when we have 3, it's 3, 3, right? Oops, I didn't put that circle at the right place. Should be 2, 2, right? And then 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, and so on. And so I can just connect those dots. And put my arrow. Now, if this had been some other function, some other linear equation, say it had been 3x or something like that, we would have gone to this point and we would have gone up 3 and over 1, up 3 and over 1, up 3 and over 1, and we would have connected the dots that way. But since it was just equal to x, it makes more sense for us to just consider 2, 2, 3, 3, 4, 4, and so on. So what we've done here, just to recap, is we've graphed each of these pieces individually. We did x squared in this portion where x was less than or equal to 1. It was equal to just the value 3 from 1 to 2, and equal to x when x was greater than 2. Last question. Is this a function? I heard a no and a yes. If you think it's not a function, tell me why.
There's like, there's an X one.
So, I want you to look here. This x at 1 isn't there. This one's not included. So those holes have to line up with one that's included for it to be a function. And you probably could have gotten that from the fact that the examples instruction said consider the function. Just for fairness. Any questions about this section? Domain and range, properties of graphs. Okay, well, it is a little bit early. That is the end of 3.2, domain and range, 3.3, properties of graphs. I will see you guys tomorrow. Have a great rest of your Wednesday.